Hi guys, so this problem is problem number 36 from chapter 7 from the section on step response of an RL circuit. So first let's describe the circuit and then go through what we're looking for. So we have a 150 volt independent voltage source. This is 5K here, this is 20K, this is 4K. Before time 0, we have a switch that's open. At time 0, the switch closes. Here we have a 75 millihenry inductor. This is 20K, a 0.5 milliamp independent current source, and a 40 kilo ohm resistor. So what we're looking for in part A is the initial current that's going through the inductor. In part B, we're looking for the steady state current after the switch closes, the final current through the inductor. In part C, we're looking for the time constant tau. And then in part D, we're going to put parts A, B, and C together to find the final current, equation, general equation for the inductor IL after the switching happens. So we're going to put it all together in part D. Okay, so the first piece of the puzzle is the initial current through the inductor. In order to do that, we're going to redraw the circuit and analyze the circuit before the switching happens. So here we have, so the circuit at time 0 looks like this: plus minus 150 volts in series with 5K, and then we got 20K here, and here we have the 4K, right? And then the switch is open. The inductor is in its steady state, DC steady state. So it's going to appear as a short. It's charged up to some initial value by the independent current source and the 150 volt independent voltage source. We don't know what that is, but it's right here as a short. So then we have here the 20K resistor, still got the 20K, and we got the 0.5 milliamp independent current source, and then we got the 40K resistor. Okay? Alright, so we are looking for that, the initial current through the inductor, which is called I0. And to do that, we're going to use the node voltage method. Okay, so I'm going to call this node VA, this node VB, and then this node I'm going to call VC. And obviously my I0, which is the initial current through the inductor, will be VB minus VA over 4K once I figure out what VB is. Okay, so I'm going to erase a bunch of this information, the initial circuit, and start writing my equations, my node voltage equations. So, first equation is at VA. So I'm going to have VA minus 150 over 5K. Then VA over 20K, plus VA minus VB, that's over 4K, that's equal to 0. Now my node voltage equations at VB is going to give me VB minus VA over 4K, which by the way is I0. And then VB over 20K, and then VB minus VC over 20K, that's all equal to 0. And here, unfortunately, I don't have advanced technology. And even if I did, I'm a little bit old school, and I kind of like the chalkboard, I have to admit. So, look back at your circuit diagram, your schematic, and I'm going to look at mine. And nodal equation at VC is going to be VC minus VB, that's over 20K. Plus, and then you've got the 0.5 milliamp independent current source going into the node. So that's going to be really a minus 0.5 milliamps, and then plus VC over 40K. That's equal to 0. And like always, we're going to put this up as a matrix. VA since I'm short on board space, well, let's just write it out. So my coefficients for VA is going to be, I am short on board space, so I'm going to add them up and then write down one number. So my coefficients for VA is going to be 1 divided by 5,000, 5K, plus 1 divided by 20K, plus 1 divided by 4K. 4K. That gives me 0.0005 for VA. And then VB is going to be negative 1 divided by 4K. That's going to give me negative 0.12325. VC. So VC, I have no occurrences of VC in my first nodal equation. And then this 150 over 5K will become a positive number on this side. So 150 divided by 5,000 will give me 0.03. 0.03. That's my first nodal equation. My second nodal equation is going to be negative 1 divided by 4,000. That's going to be for VA, I'm going to have negative 0.00025. And then for VB, I'm going to have 1 divided by 4K plus 1 divided by 20K plus 1 divided by 20K. And that will give me 0.00035. And then for VC, I have negative 1 divided by 20K. And that will give me negative 0.12345, and then no constants. Now for my last nodal equation, I have 0 occurrences of VA. And then for VB, I have negative 1 over 20K. So negative 1 divided by 20K is going to give me negative 0.1234. 4 zeros and then a 5. And then for my VC, I have 1 divided by 20K plus 1 divided by 40K, which gives me 0.10075. And then on the other side, this 0.5 milliamp will come on the other side as a positive 0.05. So that's going to be 0.5e minus 3. So that's going to be 0.10005. So now we're going to put all of that into our simultaneous problem solver. That's 3 equations and 3 unknowns. So I got 0.00005. and then negative 0.00025, 0, and then 0.03. Then negative 0.10025, and then 0.00035, and then negative 0.00005, and then 0. And then final line is 0, negative 0.00005, and then 0.00075, then 0.0005. Solve it, and we come up with the 3 values. Okay, so what we come up with is VA is equal to 100 volts, and VB is equal to 80 volts, and then VC is 60 volts. Now, go back to your schematic right here, right? So the current going through the inductor, the I naught, the initial current through the inductor is VB minus VA. That's over 4K. So that gives me VB is 80 volts and minus VA is 100 volts over 4K. 4K. That gives me, so 80 minus 100 divided by 4K. It's going to give me negative 5 milliamps. So let's put the A over here. I naught is equal to negative 5 milliamps. Okay, so that's one part of finding the general equation. Now, part B, we're going to find the final equation. So, we need to find the final current through the inductor. So let's draw the final current. Where's the initial diagram? So now, that switch closes, shorting the circuit entirely from the 150 volt independent voltage source, the 5K, the 20K, and the 4K. So now those are no longer part of the circuit. So here's the switch, it closes, right? Now the circuit is in its final, the steady state, which means it's been closed for a long time, right? So here our inductor is going to be a short. It's going to receive a final charge of some kind from that independent current source. So that closes, and so this is 20K. This here is 20K, and then we have our 0.1 milliamp independent current source here, and then we have the 40K here. This is what the current looks like in the final, after the switch is closed for a while, and we are looking for I final. Now notice that we have a short circuit in parallel with a 20 kilo ohm resistor, so 0 in parallel with 20K is 0. So this completely shorts out that resistor, so that resistor goes away. Okay, now to find this, we're going to use, we could use a couple of things. We could use current division, or we could use node voltage, or we could use mesh currents. I chose to do it by node voltage, so I call that V sub S. And node voltage, just a reminder in case you forgot, is an application of KCL. It says that Kirchhoff's current law says that the sum of all the currents leaving a node must equal 0. So current is V over R. So the nodal equation there is Vx over 20K minus 0.5 milliamps plus Vx over 40K. All that is equal to 0. So then Vx 120K plus 1 over 40K, that's going to equal 0.5 milliamp. So then Vx is equal to, let's figure it out. So we got one divided by 20K plus 1 divided by 40K. Alright, so then we got 0.5 milliamps. Divide that by that. So then this tells me that Vx is 6.6667 volts. Alright, that's not what I'm looking for. I'm looking for IF. So IF is going to be, the final, I final is going to be Vx over 20K. So I'm going to take that and then divide that by 20K. And that tells me that the I final is 0.3333 milliamps. Right, so that's part B. I final, the final current going through the inductor is 0.3333 milliamps. Okay, that's part B. Now, part C is finding tau, and tau is L over R. So which R are we talking about? We're talking about this R, that R. We're talking about the R after the step event, which is the switching. So the switching has closed, and the R that we're talking about is the resistance seen by the inductor. So that means we're always going to come back with R Thevenin. If there's multiple circuit elements, to find tau, you always have to return to your Thevenin equivalent circuit. So tau then, tau is L over R, Thevenin. I'm going to return to this circuit here, but now to find our Thevenin, right, I'm going to open the load. Here it is. I'm going to open that inductor and I'm going to see what is the resistance that's seen there. But now I have to restore that one that was shorted out because this is open, this becomes relevant again. So let's restore that 20K, right? So here's my inductor, I opened it, so my V Thevenin is going to be right here, V Thevenin. And that 20 kilo ohm resistor is now a relevant factor. We're going to do node voltage again. So we opened the inductor and then we're looking in here to see what's the resistance seen by the inductor. So V Thevenin, node voltage at V Thevenin is going to be V Thevenin over 20K plus V Thevenin minus Vx over, what was that? 20K. 20K plus, oh that's it, that's equal to 0. Now node voltage at Vx is going to be Vx minus V Thevenin over 20K plus V minus, right, because we got this current going into the node, minus 0.5 milliamps plus Vx over 40K. All that is equal to 0. Now, let's make our matrix. We got V Thevenin, Vx is equal to, so here we got 120, 1 over 20K plus 1 over 20K. And then for Vx, we have negative 1 over 20K and no constants. And then in the second equation, we have for V Thevenin, our coefficient is negative 1 over 20K. And then for Vx, we have 1 over 20K plus 1 over 40K. And then this will come over on this side as positive 0.5 milliamps. Okay, so now let's go ahead and input that matrix into our matrix solver. So we got 2 equations and 2 unknowns. 1 over 20K plus 1 over 20K. And then negative 1 divided by 20K, and then 0. Second line is negative 1 divided by 20K, and then 1 divided by 20K plus 1 divided by 40K, and then 0.5 milliamps. Okay, so then this tells me that V Thevenin, so what my matrix tells me is that V Thevenin is 5 volts and Vx is equal to 10 volts. Now we needed V Thevenin because we were looking for our Thevenin, right? And we can't directly know what our Thevenin is. The way we find our Thevenin is by using the relationship between the definition of our Thevenin. The definition of our Thevenin is it's V Thevenin over I short circuit, right? And I short circuit is the short circuit current going through the inductor when the switch is closed, and that's going to be I final, right? Because after the switch closes for a while, we know that's the short circuit current going through it. So then this is going to give me 5 volts divided by 0.3333 milliamps. So we go 5 divided by 0.3333, and that tells me that our Thevenin is 15 kilo ohms. Okay. So now we know what our Thevenin is. We were really looking for the time constant, and tau is the inductance divided by our Thevenin. So the inductance was 75 millihenries. So 75 millihenries divided by 15K. So then I'm going to go 75 millihenries, divide that by 15K, and that gives me 5 microseconds. So the third part of this is going to be 5 microseconds. That's the value of our time constant. Now we're going to put it all together to find the general equation for, this is the general equation for the inductor after the switching occurs. The general equation is always, so IL after the switching closes is always the final plus the initial current minus the final current times e to the minus t over tau amps. Okay? So now we have all of the things, all of the components that we're looking for. So it should be, I final is 0.3333 plus negative 5 milliamps minus 0.3333 e to the negative t over 5 microseconds milliamps. Okay? So then put all that together. IL of t is 0.3333 minus 5.3333 e to the 200,000, negative 200,000 t milliamps. And that is the answer to problem number 36 from chapter 7. Remember, if you got help, please like the link on the Facebook for this problem so that your friends find the page. All right, good luck, you guys.